Okay, students, so today will be lecture 7, and this will cover the second digestible portion of chapter 2. These are big chapters, so they cover a lot of material, each chapter certainly. Chapter 2, we started learning about how to create a epsilon that is negative, and for that you try to mimic what's going on with a metal by having an electric plasma. So there's a couple of ways to do that. One where you can have a metal. However, a uniform metal leaves no space to put in structures that create a negative mu, a negative magnetic permeability mu. So you got to do something else. You got to free up some material in there, free up some space in there while maintaining that negative epsilon. One way to do that is to try to use waveguides, potentially. And the walls of the waveguide basically maintain that property of a negative epsilon. And so the first thing we did was looked at one waveguide, then we looked at an array of waveguides. The next step in that was to get rid of most of the metal walls of the waveguide, but keep the wires, sort of represent the corners of those waveguides as wires. And then you have the mesh wire grid. And the mesh wire grid has a negative epsilon. But plenty of space within that to have structures that produce a negative mu. So now we have to look at a negative mu material and how we would make that. Now, so with this, and that's the second part of chapter 2, synthesis of magnetic permeability structures. So it was first hypothesized by Wilhelm Weber in 1852 that closed circuits at the molecular scale would induce magnetic fields in the opposite direction compared with the exciting or external magnetic field. All right. This is purely a consequence of Faraday's law, and so that when you have a change in the flux, you have the circuit that wants to fight that, and so it will create a magnetic field in the opposite direction. All right. And so they were trying to figure out if it is large enough to produce a negative polarizability. So the magnetic polarizability of a lossless conducting ring along its axis is given by this right here. M sub z, so magnetic polarizability in the z direction is linearly proportional to B in the z direction through this alpha term, the polarizability, which itself is a tensor. And in this case, it is the ZZ tensor component that connects B sub z with M sub z. All right. And it's equal to pi squared times r to the fourth over L, where r is the radius of the ring, and L is the self-inductance of the ring. All right. So that is a magnetic polarizability. However, it was believed that this diamagnetic effect is not nearly strong enough to produce negative values for the magnetic permeability mu, because the self-inductance for the ring is given by this. And I may have you derive this for a homework problem. L is equal to mu naught times r, the radius of the ring, times the quantity, log, of 16r over d, where d is the diameter of the wire, minus 2, closed quantity. All right? So that is the self-inductance of the ring. So the question then is, can we get this to be negative? All right. Okay. So, well, to do that, we have a couple of things to play with. Not very much, really just R and D in this equation here, R and D. So this is the geometry of the situation right here. And so if my ring is the smallest possible radius, then R min is going to be D over 2. All right, D over 2. So we can plug that in, R min, and so the smaller log is, the smaller the argumental log, the chance that we'll be able to get this, the smaller the quantity log x. So the smaller x is, smaller log x is. All right, it's a monotonically increasing function. So we want to get this minimized. To minimize that, we minimize r. But however, the smallest r we can have is d over 2. So we have so here and here we have the smallest this can be is 16 times d over 2. The d's cancel, and you have 16 over 2, or log 8, and so r has to be equal to 0.4618. R over d has to be equal to 0.4618, or r is 0.4618 times d. All right. However, going back up here, the smallest we can have for r is 0.5d. It can't be smaller. And 0.4618d is smaller than 0.5d. And so having this as a negative value, this entire thing as a negative value, is not possible. So L will always be positive. Therefore, the mu will always be positive, and you cannot get diamagnetism, certainly strong diamagnetism, from a metal wire. It's just not possible. So L is always greater than mu naught times R for any realistic value of R over D. So the magnetic susceptibility of an arrangement of rings can be estimated as, so we're going to extend this. So the magnetic susceptibility of an arrangement of rings can be estimated as chi is equal to mu naught alpha zz over V, where V is the volume per ring, and you basically look at 2 times R, 2 times 2 times R times 2 times R. Where r is the radius of the ring, and so that's it. The rings are so close together that they're basically touching each other. So the volume per ring is 2r to the cube power. You can put that into here, and so for any realistic value of r over d, the mu alpha zz is equal to pi r cubed. So with this and with v, you get this chi is approximately equal to 1. Okay, so chi, the magnetic susceptibility, is pretty close to 1. So it's not very large at all. So thus, obtaining a negative value for mu using an array of rings is not possible. All right. So this is the problem people had up until Pendry and Smith. That just using so in nature we couldn't find a material that had both epsilon and mu being negative. We had materials with epsilon being negative; those are all around. We had a little bit, some materials with negative mu, diamagnetic materials, but those weren't very strong negative U values, and not very large negative mu values. But we did not have things that had both negative epsilon and negative mu. And the rings wouldn't help either. That's what the first three slides were all about. So where did we go from here? So this is the state of things before Pendry and Smith came along. And then they said, well, and actually the step before, Shulkinoff, a famous guy, you'll remember Shulkinoff came into our class in advanced electromagnetics for engineers, where we had Shulkinoff functions and various things. So he did a lot in electromagnetics. Shulkinoff proposed inserting a capacitor in the loop. So really I have to find out exactly when this is, when actually he did propose this. So I have to dig this up. It's going to be interesting. He was a very smart fellow. So he proposed inserting a capacitor in the loop. Upon doing so, the alpha ZZ changes. So it's no longer just this and this part of the term, but you have this in there as well. All right? Where omega naught important, so this is basically what he said. Put in a capacitor into the system and you're making it a LC circuit. And with an LC circuit, you have a resonant frequency that is equal to 1 over square root L over C. Thus for omega being slightly higher than omega naught, then alpha ZZ becomes large and negative. And so you can then get a negative magnetic permeability. But then people thought, okay, well, we'd like to now implement this in the visible spectral regime, the infrared spectral regime, and even the microwave spectral regime. You know, all sorts of spectral regimes. But actually, how do we do this? It turns out to be really hard to make these three-dimensional types of structures like this in any convenient method, and in the optical regime, in the IR regime, any method at all. So how do you actually make it? But regardless of that, Cholkanoff should get some credit because he did figure out the first way to actually make it a mu. And quite often his name is forgotten in metamaterials. So this would work. But Pindar came up with a better idea for making it. He said, instead of doing what's called this lump capacitor, where we have the capacitance all in one area right here, how about we do a distributed capacitance by just putting in an accompanying and adjacent metal structure all along the ring. So here we go. But how would you actually fabricate an array of these LC circuit rings with these lump capacitors? Hard to do, all right? Using printed circuit board fabrication techniques, you can create a distributed capacitance with a metal structure adjacent to the original metal ring. This is what Pindar did in his proposed edge-coupled split-ring resonator structure. All right, and so this is what it is. So we have the original ring. Either one of these can be viewed as original, and the other one would then be the add-on or adjacent one. So we have, let's say the inner one is the original, and then around it we put in the adjacent one. And so we have this metal dielectric metal interface everywhere around here, metal dielectric metal. And so but it's distributed over the entire structure. So it is a distributed capacitance as opposed to a lumped capacitance, a discrete structure within the structure that has the capacitance that's lumped versus a distributed thing throughout the entirety of the structure. This is distributed. And notice that this is all flat, so you can use these 2D printed circuit board techniques to make this quite convenient. So bingo, we have it then. Still the resonant frequency is 1 over square root of LC, but now the trick is just to find the L and C. So there we go. So this is a solution. Cholkanoff introduced said let's split it, put a capacitor in there, and we get a resonant frequency. According to this, Pindar came along and said, well, this is a more convenient way of doing it, and bingo, we're off to the races. All right. Okay, but before we follow with Marquez in his book, let's highlight something that we haven't stressed up until now with this major change. So let's compare the two alphas. Before launching into it, let us highlight an important thing that we gave up when a capacitor is introduced in the structure. Okay, so here are the two alpha values, here and here. And you'll see that we have this portion of it right here with the -1 and all that. So now we have So this note has no frequency dependence. L is not frequency dependent in this structure. But and there's no other frequency dependence that comes in through any other factor in this ring alpha. But for the LC circuit alpha, L may still not be dependent on frequency, but the frequency dependence certainly comes in here and is very strong right here. All right. So alpha Z of the ring is not frequency dependent, whereas it is for the LC circuit. All right. So what does that mean? Well, that means that the properties that we're shooting for, ultimately the negative magnetic permeability, is not going to, that it may not happen over all frequency ranges. And in particular, it may only happen over a very small bandwidth of frequencies. And that's what we find, that all of these materials from Pendry on, except for a very small subset now that we're starting to figure out how to do, all of these materials demonstrate their metamaterial behavior, namely negative epsilon and negative mu, for very small bandwidth ranges. And so we've given up the broad bandwidth operation of these materials, these metamaterials, for their metamaterial properties, namely negative epsilon and negative mu. So thus, we are giving up negative mu over broad bandwidths. Negative mu will occur only over narrow bandwidths at the resonant frequency, at and around the resonant frequency. All right. This issue has plagued metamaterials ever since. And so now the whole big thing is trying to figure out non-resonant metamaterials. And for a lot of applications, not all applications, certainly some applications still very specific wavelengths are important and others are not. But there is a tremendous amount of interest in research dollars going into figuring out how to make non-resonant metamaterials. One potential thing to do is go back to the ring and see if there's anything else we can do with the ring itself to get negative mu. So one interesting thing would be to go back to this equation, rederive it, look at what assumptions were in place to derive, if there were. And so there'd be an interesting homework problem, something I'm certainly going to look up. I'm now curious about it. And can we add additional loops? Can we add material within the ring? Can we then do something else to adjust this equation so that we can eke out a negative L? So, interesting. So, we have, for the sake of getting the negative mu, we have taken up dispersion, meaning frequency dependence. Okay. So let's now move forward with the edge-coupled SRR, EC-SRR. The EC-SRR was introduced by Pendry in 1999 as a practical way to achieve negative mu and epsilon over narrow bandwidths. It produces a negative mu when a component of the magnetic field is along the z direction, i.e. the ring. Okay, so just as you would expect using Faraday's law, when you have a z component of the magnetic field going through the middle of the ring, you're going to have a time-changing flux of that, and the ring itself will induce current in the rings that fight that time-varying flux. And that induced magnetic field will be in the opposite direction of the exciting field, and so you will be fighting that magnetic field, almost canceling it out. Okay, so but however, with the nested rings, you will get this electronic charge configuration. When you have positive charges on one ring, it will induce negative charges on the other ring adjacent to it. Just a pure capacitance effect. All right? And then here, you'll have the image charges here, the exact opposite. So when you had negative up here, you have positive down here. And so you will get, and this is a dipole. This is an effective dipole going from negative to plus, from negative to plus. And so you have two electric dipoles here, and you have a magnetic dipole. So this one structure reacts in a similar fashion compared to an electric dipole and magnetic dipole. All right. So we'll get back to that in a moment. Get back to the dipole picture of this. So the equivalent circuit is easy then. We have two capacitors in series, potentially some resistance because of a lossy regular metal, and then inductance due to the ring structure. So L is the self-inductance, where C total is equal to C over 2 because these are in series. Each C is equal to the capacitance per unit length of the slot. So we're going to assume that the space between the rings is very small. The space between the rings is very small. Therefore, you can assume that they're pretty much straight lines or parallel plate capacitors almost, but they're not. They actually have a length of pi times r and pi times r for the two capacitances. So we have pi times r times C pole for one capacitor, pi times r C pole for the other capacitor. They're in series. The capacitors in series, if they're the same capacitance, they have it. The capacitances, and so this is what we have. All right, and this is derived in the appendix of Marquez, but you could do it yourself potentially. It's quite difficult, or you could pull it up. And if it's not per unit length, I mean, if your material in the middle or your space, if D, the spacing between the rings right here, is not small, then the formulas become more complicated, but still derivable. All right. So the equation describing the situation, so the equation of state, but you're really just summing the voltage drops and gains around the wire, is equal to this. It's C over 2 on the denominator, so the 2 can come up here. So you have 2 over J omega C. So this is for the capacitance part, what's typically done for the capacitance. And then you have the J omega L times I, and is equal to the excitation. So this is the equation that describes the situation. Of course, at resonance, resonance occurs when you do not need an excitation, but you still have something going on with the structure. And so therefore you want this to be 0, you set that to be 0, you find the omega, which establishes that to be 0, and you find it's equal to 2 over LC. You can put in what C is in terms of C pole per unit length, so it's 2 over pi RC pole times L. All right, so far this neglects any resistance in the wire or other sources of capacitance. All right, this is only assuming the capacitance between the two rings, and not right here, and not right here. And so later on, structures that were developed later on said, okay, let's not forget that. Why don't we actually make these capacitance to be large? And we might, if we can make these large enough, especially say this one, potentially we can get rid of the middle ring itself in its entirety. Yeah, maybe. It might make the analysis simpler. Okay, so then Marquez has some nice convenient formulas for L and C. So L is the average self-inductance of both rings, and so this is what we have. L is given by this, and where A is this and B is this, and capital B is equal to this interesting function, that has within it the Struve functions and Bessel functions. Well, most all of you have heard of the Bessel functions, but in all honesty, the Struve function, this is the first time I've seen the Struve function. So quite an interesting integral here. And likewise, C-pole is equally interesting. And it is equal to this function, the E sub E, epsilon sub E, F is a function of K, where things are nested several layers deep in definitions. So this epsilon E is given by this right here. This is the epsilon of the substrate, epsilon naught, F of K and F of K1. K is equal to A over B. A and B are given up here again. D is the width between the slots. My K1 is given by hyperbolic signs. T is the thickness of the substrate. A and B are up above again. This K prime is, so we have K, we have K prime, and then we have finally the F of K right up here. And so this is what we have in terms of K prime, and K prime is equal to 1 minus K squared. So it looks long, but it really is not. You just put it in MATLAB and plot it out. And it's actually quite easy to do. It's just a lot of nested definitions. So not all that difficult. But in the end, it gives you both L and C. I haven't checked within MATLAB if they have a library that gives you the Struve functions. I'm hoping it does. I'm going to be checking once I get done with this. Otherwise, we'll dig up a MATLAB community program that does this. Okay, so we'll be able to find L and C pole, and that's what we need to find the resonant frequencies and so forth. So, if the EC SRR is excited by a magnetic field, then we can find this external excitation. It's the potential applied due to the external excitation, which is the minus the time derivative of the changing magnetic flux. Take that time derivative, assuming a sinusoidal wave, and it's minus j omega times the flux. All right. Then the voltage drop equation leads us to this equation here. All right. So we're going to be using that. We already have shown that the EC SRR behaves as a capacitively loaded conducting loop. It is a magnetic dipole with the resonant magnetic polarizability of alpha ZZ in it. But current in the EC SRR can also be produced by an electric field in the y direction. All right. Thus, M sub Z is given by both of these components. A component due to the magnetic external magnetic field producing it. That's the first term. And by a external electric field in the y direction producing it. And that's what this term here is. All right? So, additionally, the EC SRR behaves like a strong electric dipole to the charge distributions produced by both E sub Z and B sub Z and E sub Y. So it also acts as a strong electric dipole. So it's going to be producing an electric polarizability P sub Y. All right? And so we express it in the same way. And we would also expect that both E sub Y and external E sub Y creates it, and an external B sub Z creates this P sub Y. And so we have the two tensor components, the polarizabilities alpha YY EE and alpha YZ EM, due to the fact that contribute to this. The M and the E state that this alpha is due to an applied magnetic field, but it is producing an electric field. That's what that means. And of course, the subscript means that it's connecting the Z component of the magnetic field with the Y component of the electric field. So, so beside all of those are resonant. The alpha YZEM, alpha YYEE, alpha ZZMM, and alpha YZEM. All right. But you also have a non-resonant piece of X that plays a much smaller role. All right. In fact, it's just there. It doesn't produce the mu, negative mu that we're looking for, but it is there. So we write it down for completeness sake as this. All right. So combining all these things, putting in what my my various values are for the alpha YZs and the alpha ZZs, we collected all the equations right here. Okay. So the only new definition, C-pole has been identified before and defined before and given before, same as L, and the only thing not given is the D effective, and that's C plus D. All right, and like I said before, there is a non-resonant electric polarizability given by this with alpha XXEE as this. Okay, but that's not really what we're looking for. It's the resonant ones. So the only other thing in here really is if we include losses into the system, it is going to broaden out the resonant frequencies. So if we include losses into the system through the metal with a finite conductivity sigma, so of the metal ring, so the metal that composes a metal ring, which itself has a thickness of H, we get L has to, wherever we have L in there, has to be replaced with L hat, where L hat is equal to the original L plus R over J omega, where R is the resistance of the ring, and depending on if H over 2 is less than the skin depth, this delta is the skin depth of the metal. If we have a very thin metal wire, then the resistance has H down in the denominator. Okay, but if it is thick, then R is equal to pi R naught, the radius of the wire, C, the width of the wire, delta, the skin depth, times the conductivity, namely the conductivity on the denominator. So that's because the current is only flowing within the skin depth on either side of the material. So the resonant frequency then changes because it's no longer just 2 over LC, but it's 2 over L hat C, where L is itself imaginary. Okay, so basically what that means is that you're not the ring is going to lose energy through thermal dissipation, Joule heating. All right. So this factor here, this all-important factor that comes into many equations, becomes a Lorentzian type of function given by this, a typical Lorentzian form. All right. So the alpha terms have this Lorentzian form right here, 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 and here. And so therefore those resonances are broadened out, but there's some absorption involved in the system. And so that's important. Both absorption is bad, certainly, but the broadening out of those resonances is a good thing. And so then you look at, well, is that trade-off desirable? Is it fine? So we want more bandwidth. Can we afford to give up a little bit of energy in the system? And if the answer is yes, then this is the way to go. So this is Pendry's big discovery, basically looking at how to mimic the negative permeability that diamagnetics have via their molecular orbitals of their electrons, but really increase it a lot, so you can have a large diamagnetic behavior. And the only way to do that is to introduce a split in the orbit and put in capacitors. How to effectively do that? Not by the way Shulkinov proposed, but in this way here, a distributed system. And then it's just working through the mathematics and demonstrating that, yes, indeed, you can get strong diamagnetism with these structures. So, okay. So that's that. We'll assign a homework set that exercises the use of some of these. And otherwise, take care.